If no, then let's go ahead. Why bandgap materials? I uploaded some paper. They are pretty very what is called important paper, right? Many people refers to this. The first two paper is about gallium nitride. The last paper is about the general ultra wide bandgap device. Okay, go to talk about this topic. Now, finally, let's go to gallium nitride, right? We have covered silicon carbide, gallium oxide, gallium nitride. Gallium nitride is very important, and this is the last thing I will cover, right? Diamond and aluminum nitride are not that important at this moment. You see, this is what do you call hexagonal structure? Remember hexagonal structure, we have so-called silicon phase, carbon phase in silicon carbide. In gallium nitride, you also have gallium phase and nitrogen phase. If you cannot see it, just look at this. This is gallium. Remember, gallium is larger than nitrogen. Nitrogen is the second row in the periodic table, right? But nitrogen is more electron negative. That's why you have negative and positive here. What is this? Do you remember what is this? When you have this plus and minus, what do we call it? What do we call this?
Polarization.
Polarization. And before that, we say this is called dipole moment, right? And you have all this polarization, dipole moment everywhere. Eventually, you get polarization charge. Okay, so in a gallium nitride, the most important thing is this. So here, I actually should not add this, right? GaN is already gallium nitride. I should not say gallium nitride crystal. But anyway, you see that I have different polarization. So on the top, X minus 1. Are you talking about this one, Elisa, or other page? Right. I will explain to you later then. So because of each of these have negative plus, so effectively, I have a negative Q here, right? Polarization charge, positive Q here. For nitrogen phase, I have positive Q here, negative Q here, right? So there's polarization charge due to dipole moment. Note that I did not apply any electric field. I did not apply anything. And we call this spontaneous polarization. The material itself just has polarization, positive and negative on different sides. Okay, that's the special thing about gallium nitride. Silicon carbide, you don't have this problem because they don't break the symmetry. Even silicon and carbon has different electronegativity, but because of the crystal structure, you don't have polarization charge. But here we say that it breaks the symmetry so that you have this negative and positive polarization charge in gallium nitride. Is this okay? Now, besides this, we can substitute gallium by aluminum. Now, this is a little bit like what we did in silicon germanium. Remember? We substitute silicon by germanium. Then it becomes silicon germanium. But here, only substitute some. Right? Maybe later you don't know what is the meaning of sub. So let me spell it out. We only substitute some of the gallium by nitrogen, by aluminum, then you will get a different material. Just imagine this. For example, here, maybe this, I remove this gallium, I put a tiny aluminum here. This one, tiny aluminum. That's it. I substitute some of them, not all of them. If you substitute all of them, it becomes aluminum nitride. Okay. Now, you ask what is X? X means how much percentage of it is aluminum. So if you want to add together, for example, 0.2, gallium, 0.8, you add together has to be 1. That's why it's 1 minus X instead of X minus 1, right? Both of them have to add up to be 1. So here basically say I have 20% of this cation aluminum and 80% gallium. And then nitride is still in the nitrogen is still in the original location. Okay, yeah. She thought that's integer. No. So this is yeah. So good point. Okay. Any questions on this? And here show you the crystal structure of the gallium nitride again, right? Same as silicon carbide. You have the so-called C plane. C plane actually did not mention explicitly. That is the 0001, right? And you also have A plane. And also here it did not show you. This is the M plane. This is the M, right? Everything is the same, right? But I want to show you that, you see, they have different lattice constant for different material. You can have aluminum nitride, gallium nitride, or indium nitride. They are all in the same column in periodic table. So the size get larger and larger. Indium is a very big atom. So that's why you see the lattice constant increases. Okay. Maybe I will just stop here. Time's up, but we are in a pretty good shape. Okay. Let me know if you have any questions. Last time, so what's so big deal? Now, this is just a reminder about the crystal structure. I won't spend too much time, but here I do want to point out that we talk about gallium nitride. Well, you can, for the same structure, I can also replace the gallium by aluminum or by indium. If you check the periodic table, this belong to group 5. I think so. No, group 3. Group 3. You have aluminum, gallium, indium. An atom getting larger and larger, right? So you see the lattice constant from 3.11 to 3.5. It's a big deal, almost 10%. 10% is enough to break anything. 10%. Try to stretch your table by 10%. You will break, right? Stretch your hand by 10%. I think you will break also. So 10% is a very big lattice difference, right? And then they also have different polarization charge. For aluminum nitride, it is stronger than gallium nitride, okay? But anyway, you just treat them as the same distance. So for example, here, this is the crystal. Nitrogen is the yellow one. It occupies this lattice side. And then aluminum and gallium can go to this part. You can have all gallium, then it is pure gallium nitride. You have all aluminum, then it's pure aluminum nitride. You can also have alloy, which I mentioned before. For example, aluminum, gallium nitride. It means that I randomly replace some of the gallium by aluminum. So I may have X can be 0.1, right? Then it means I have 10% of the atom that is aluminum. So among 100 cation, not counting the nitrogen, among 100 this purple or blue big atoms, 10%, 10 of them are aluminum. And they have very different property. Any questions? So this is the structure. So what's such a big deal, right? Let's just introduce to you. We can form gallium nitride heterostructure. Basically, it is like this. I can form a layer of aluminum, gallium nitride on top of gallium nitride. This is heterostructure. When you say hetero, it means that they are not of the same material. They are hetero. And because aluminum is smaller than gallium, it has larger band gap. So first of all, you can see that I have a change of band gap from top to bottom. And you're also going to confine my electron. I'm going to show you later, right? But basically, this type of heterostructure has this benefit. First of all, electron effective mass is 0.22. Okay, this is higher than the gallium arsenide. It's not that good, but that is okay. But it has the high peak electron velocity, saturation velocity, high thermal stability, high large band gap. So it's very useful for microwave power device. So now the gallium nitride is used a lot in the microwave, the base station, okay, 5G, okay. We talk about polarization, right? There are two types of polarization. One is spontaneous polarization. That what does it mean? This is just like in the slide 5. Right? It has polarization naturally. Now, let me ask you, if this one has polarization due to the dipole moment, what if I stretch it? Let's say I stretch it vertically longer. Do you think I have more polarization or less or the same? Here I tell you that because of different electron. Let's say again.
You have more.
More, why?
Since you're stretching it vertically, there's an opposite force going to the other direction, hence on the same direction on the dipole, making it more.
Exactly.
Because
they have two charge, you stretch it more, then your distance will be longer, dipole will increase. Okay, so polarization will increase. So what does it mean? It means I have more polarization. Okay, I should not say more. Let me just say polarization changes due to mechanical effect. And this is what we call piezoelectric. Piezo means mechanical. Electric is polarization. So you squeeze it, it's going to generate more charge. And this is what we use for some material. We use this to generate electricity by applying force to it. Okay, piezoelectric effect. So polarization comes from two things in gallium nitride device. One is by itself, it has spontaneous polarization already. You do nothing to it, it is relaxed, no stress, but it already have polarization charge. Then if you try to stretch it, it has more or less polarization charge. And then with this, later I also show it's going to have so-called 2DEG. This one you see very often, means two-dimensional electron gas. We talk about different 3D, 1D, 2D density of states before, right? This structure is going to give you something called confinement, and then you are going to get electron gas. Okay, so these are few concepts you don't understand too much now. Let's go ahead to talk about, first of all, how do you get the 2DEG? Now here to remind you, for gallium nitride, if you have gallium phase, you have negative polarization charge on the top, positive polarization charge in the bottom. If you're nitrogen, you have positive polarization and negative polarization at the bottom, nitrogen phase, I mean, right? So here you see that we have N phase, gallium phase, nitrogen phase, nitrogen phase. And one thing also I need to tell you, earlier I say that for polarization, aluminum nitride is more than gallium nitride, just because aluminum is more electropositive than gallium nitride, right? So the electron crowd will be even shift more to the nitrogen, right? This is what I'm talking about, the electron crowd, right? Because aluminum is very positive, so the electron even shift more to the nitrogen. Is that okay? So just a very simple thought, if that is the case. Now, let's see, this is how we grow our structure. If for gallium nitride, for example, let's only pay attention to gallium nitride here. So on the top, what charge do I have at the top of the gallium nitride when it is gallium phase? What type of
Negative.
charge? Say again.
Negative.
Why negative?
On top of the gallium. Oh, gallium nitride. I was just following the picture on the GaN phase.
You're right. I just wanted to say this is gallium phase, right?
It was because of the GaN phase. I was going to say that it's negative on top and positive at bottom.
Right. But how about the bottom of aluminum gallium nitride here? What is that?
It will be positive because of the GaN phase.
But remember, I just told you that aluminum nitride, if you're aluminum, you have more polarization charge. So at this interface, I have this plus charge. Okay? So what happened? When I have plus plus and minus minus, what is the net charge here?
Neutral.
I have 3 plus and 2 minus. What is the net charge?
1 positive.
1 positive, right? So then it means going to attract electron. So you are going to have electron along this interface. That is how you generate the channel in gallium nitride device. Okay? For nitrogen phase, what is this? Can you tell me what is the charge on top of gallium nitride? Now it's nitrogen phase. Positive, positive. Then what is that at the bottom of aluminum gallium nitride? Sometimes we call it all-GaN. Negative, right? But more, because again, aluminum nitride has more polarization charge. So the effect is what? What is the net charge here?
Negative.
1 negative. So it's going to attract what? Holes. So this type of structure naturally is going to give me what we call 2DEG, two-dimensional electron gas at the interface. This is 2DHG, two-dimensional whole gas. It's very conductive. It attracts a lot of carrier there. Okay. Now let's do one more exercise. How about this one? What is the charge here on top of aluminum gallium nitride? Here. What is that? Positive or negative?
Positive.
Positive. You have more. How about here? What do you have? Positive or negative? Gallium nitride on the bottom.
Negative.
Negative. So all together, give me 1 positive. So it's going to have electron or gas. Going to attract electron or gas. Or a hole.
Holes. Oh, electrons.
Electron. Now, do you see that how we can form a continuous layer of electron gas? We can either grow aluminum gallium nitride on top of gallium nitride using gallium phase wafer, or we grow gallium nitride on top of aluminum gallium nitride using nitrogen phase wafer. I also get the 2DEG. Okay. If you want to have 2DHG, grow gallium nitride on gallium nitride, aluminum gallium nitride on gallium nitride, but use N phase. Or here, let me show you. I'm not going to ask you. I have the negative charge here, positive charge here because it's N phase. So this one is going to attract 2DHG. So this is very interesting. We can grow multi-layer of 2DHG or 2DEG. They are very heavily high concentration electron and hole gas. Okay. Any question about this?
Yeah, those mole fractions that are under the GAM phase, N phase, does that have an impact on the 2DEC and the 2DHG formation?
They will impact how much? So this is going to impact the piezo polarization. This one, they are going to create stress, which we are to discuss later. Here, we just take it for granted, saying that I have this just a initial exercise to recognize where is the positive and negative. They will impact, yes.
Okay.
Now, before I continue, I want to review, right? I don't know if you learned this before, but doesn't matter. We are not going to test you. But there was a device called MOSFET. What does it mean? It means modulation doped FET, or it is called HEMT, high electron mobility transistor, or it is called HFET, Heterostructure FET, field effect transistor. Now you start seeing something very similar. We talk about gallium nitride, we say it is HEMT. Oh, this is also HEMT. What does it mean? We just talk about heterostructure. Oh, this is also heterostructure. What does it mean? And what does it mean by modulation doped? So this is an old structure people have been using in RF using gallium arsenide. And now what do you see? This one doesn't have polarization charge. Equal gallium arsenide here. On top, you add this also a barrier called aluminum gallium arsenide. Very similar. The only difference is that this is nitrogen. This is arsenide. That is hexagonal. This is cubic. Okay, this is just like, not, this is cubic, what we call word side structure. Okay. How do we form the channel? You see the source and drain. Okay, let's ignore it. We know it's heavily doped. And you form the channel by doing this. This one is heavily doped with electron. So if we try to draw a band diagram, cutting here, A to A dash. So A to A dash. Before they are contacted together, aluminum gallium nitride has a wider band gap. I mean, aluminum gallium arsenide, all gas, we call it all gas. And then gas, which is GASS, right? Gallium arsenide, it has a narrow band gap, but it is undoped. So Fermi level is in the middle. How do you draw the band diagram when they are touched together? When it is zero bias, what happened to the Fermi level? Do you still remember when it's zero bias?
Constant everywhere.
Yeah, this is very important. Once you draw out it is constant, the rest will be easier. Far away, it is still like this, right? Far away from the interface. But then we know that there's a discontinuity. So if you solve for Poisson equation, you will see something like this, right? Okay. You need to keep the distance, right? I think I did not draw it well. You need to keep this distance the same, okay? So in order not to confuse you, let me draw it better. Okay, that would be better, right? So this is delta V. This is delta V. Let me delta V conduction band. This is the difference in their electron affinity. Okay, same here, you have delta V valence band. Here you have a straight line, also delta V valence band. The point is this: do I have a lot of electron here? I claim that a lot of electron. Do you agree? Do you agree that I have a lot of electron in the deep over there? Anyone?
Is gas?
Say again?
Is that the electron gas that's represented?
Electron gas, yes. I want to ask, do you agree and why I have a lot of electron there based on this band diagram?
Because the conduction level.
Say again?
The conduction level is less than the Fermi level.
Very good. Because now the Fermi level is about the conduction band. Just solve the equation, you get a lot of electron. That is one thing. Second thing, it is confined in the well. Correct? Because once you just leave this part a little bit, your band goes up, I don't have electron. The electron cannot move to other places. Correct? But where does this electron come from? Remember in your all the study, you need to add the doping. Here it is undoped. Right? All the impurity are here. Impurity. All the impurity are in the barrier. The electron cannot feel them. They are far away. Okay? So 1 plus 2 give you 2-dimension electron gas. That's one thing. And that's why it gives you the name HFET. Okay? And 3 is undoped. So you have high mobility. So that's why it is called high electron mobility FET. Or it is called modulation dope FET. The doping is not inside this region, it comes from other places. Right? So I don't want to go too deep. Basically, this structure can take you 2 classes to discuss in details, right? But this is not our purpose. But I remind this because later you are going to, even your interview, people talk about RF, they talk about HEMT. Don't confuse with gallium nitride. Ask them, which HEMT are you talking about? Both of them are HEMT, but they share the same idea. They form 2-dimensional electron gas at this hetero interface. The only difference is that one got this formation of electron by having heavily doped in the barrier, but still high mobility because these impurities are not close to it. For gallium nitride, it got this high electron density by polarization charge that we just discussed. I did not dope anything, remember? I only deduced that I have electron gas here because of the polarization charge difference. Here I have the electron gas here because I have heavily doped barrier. If I don't have heavily doped barrier, this is not going to bend down. You just try to draw the band diagram. If the Fermi level is here, you just don't have this conduction band bend down. Okay, so you can get confused. But both of these are important nowadays. Okay, any questions? So I call this review, I assume you learned that before. Maybe you don't. If you don't, you can forget it. I don't mind. But if you see this, I hope that you can link to it. Do not suddenly feel that why people talk about HEM, gallium arsenide, HEM, why completely different from what I'm talking about. Because this one rely on doping. Same structure, same heterostructure, arsenide instead of nitrogen. But the doping is due to impurity, modulation dope. That's why it's called modulation dope. The gallium nitride we're going to study is due to polarization charge. We don't dope it, but because of the crystal property, it has polarization charge and give us the electron 2D EG. Right? But two things very important. You need to know that I have a lot of electron. This is no kidding, a lot. You'll see that later. Confinement the well, that one is 2D and high mobility. These are the three characteristics of both devices. Okay? Question?
So the majority carriers are responsible for current flow?
The majority here we don't talk about majority. This one just band, and even it is N type or P type here is not important anymore, right? It bend and then it form the electron over there. Yeah, you can say majority, but majority in the sense that it's the same type as the barrier. Yeah, so the electron here is responsible for the flow of the current. Do I answer your question?
Yes.
Okay, good. Okay. Now I just want to review mobility a little bit, right? Just want to show you, this is temperature, this is mobility, right? Why we say that the mobility is high? If you have a high doping, you get this impurity scattering. Right, so you have low mobility. If I reduce the doping to here, you see the mobility goes up, but when the temperature goes down, it still go down again. And this is why this again is due to impurity scattering. Okay, then why it goes down here? This is because of the phonon scattering. Right. If we can have this modulation dope channel, you see that when I reduce the temperature, it is not suffer from impurity scattering because we have very tiny doping. So that is an explanation, right? Although we don't have much time, but I feel that maybe some of you still not familiar with this impurity scattering or phonon scattering. Let's spend a little bit more time on this. These are the lattice you have, right? And you are the electron try to travel through. What is the meaning of phonon scattering? Phonon scattering means at high temperature, your lattice keep vibrating. So sometimes it may come here, sometimes it may go here, right? At high temperature. Then what happened? Of course, you will keep locking on the atom and then you lose energy. That's why mobility goes down. Is that okay? This is phonon. Any question on this? Phonon scattering.
Professor, what happens like when the electron pass? It gets disturbed with lattice.
Say again, I cannot hear clearly.
The phonon thing, can you please?
Phonon, I'm saying that these are the atom. The atom can move when the temperature increase, they vibrate. And then when your electron try to go through this material, you get knocking by this atom. That's why you slow down, so you have lower mobility.
Okay.
Make sense?
Thank you. Yeah.
Now, what is impurity scattering? You have some big atom or small atom also, right? But it's in quantum mechanical sense, you will feel the scattering. But let me just give you the big atom. What happened? if you have impurity. They have charge to it plus. I should not say bad. I'm very bad. I should not say that. Let's just say same size, but they have charge. So what happened? You're going to attract my electron, and that is scattering. Of course, we need full quantum mechanical treatment in solid state physics to derive this. But let's just think about it affecting me. Okay, so this is the impurity scattering. Okay, if you are not pure, then when I go through this array, I will get more scattering. That's why I slow down. And you see that impurity scattering is worse at low temperature. Do you see that? Mobility goes down when you have a lower temperature. Why is that? You can think of this. You are traveling slower, then you get affected by the plus charge more. Think about you travel very fast, right? You don't feel it so much. That's why high temperature, impurity scattering is less. Okay, this needs some time to digest. If you have time, try to digest this. Okay, any questions?
Professor, this when the electron travels through vacuum, we don't see this impurity scattering effect, right?
Yeah. If you vacuum, you even don't have phonon.
Yeah, and then on the
But
vacuum,
solid state.
The electron used to travel through the vacuum. So if we use a vacuum tube, so we're expecting a high mobility without this type of effect.
In vacuum tube, you even don't talk about mobility because there's no scattering, right? Mobility is what? Given an electric field, you travel at a certain velocity. Isn't F equal to ma? If I have electric field, I expect my velocity keep increasing while you tell me travel at a constant velocity. That is because you keep losing energy by scattering. So if in vacuum, you apply electric field, electron will keep accelerating until it reaches the light speed. Okay, of course, we don't accelerate to that. So in vacuum tube, our equation does not have mobility concept. In the old time when we do vacuum tube, it will just travel and actually keep accelerating, and other effect will come in. For example, electron-electron scattering. You have so-called space charge. Because now you fill up the vacuum with electron, it's more difficult to inject more electron. So you slow down the electron. That is what they call space charge transport. But this is a great question. It brings out that what is the meaning of mobility? Mobility is an averaging effect. So now go back, we talk about ballistic mobility, remember, before the midterm? Ballistic mobility is when your channel is so short, I even don't feel scattering before I reach the string. So I actually don't have a real mobility, but we come up with an effective mobility, or we just call that ballistic transport. Do you see what I mean?
Yes. Okay.
Make sense?
Yes, it does.
Yeah, very good question, right? So don't take things as it is, right? We keep talking about mobility, and if you don't ask this question, then one day you will break down because you find that we are talking about nano device. How come there is mobility or there's no mobility, right? That this concept will come up nowadays already. Yeah, so this is a very good question. But if you can ask the question and answer this question, then you kind of understand what is mobility. Okay. So now I want to, hold on. Okay, sorry. Now I just want to explain something regarding the spontaneous and piezo polarization. I already told you, right? By just having the lattice itself, right? We already have polarization charge. And this is called spontaneous polarization. What if I string the lattice If I string the lattice under stress or under strain, then I have extra piezoelectric polarization. It's a very complicated theory, not complicated, but a lot of math. But it gives us the equation. Basically, in this class, I only ask you to look up the table. You have so-called E33. This is called piezoelectric constant. It relates your string in the z direction to how much piezoelectric electric effect you have. E31, it relates how the string in the xy direction is going to change your polarization. Or just an equation, take it for granted. But let's go back. What is string? We learned that before, remember? We did learn that before in silicon germanium, in FinFET. It is just the new lattice constant, C. Divided by the C0 equilibrium lattice constant, okay? Now, I even can tell you can forget this equation. Finally, come up with this equation, okay? So remember, in hexagonal structure, we have two lattice constant because you have a vertical and also a horizontal part. This one is C, okay? And this one is A. Let's go back to this picture. Do you see that this is C and this is A, right? So actually I draw it wrong. A should be the edge. This is A. So basically you want to find out how the A changes and then multiply by this parameter. And this is the table. It gives you all of them. So the only thing then, why do we have a string? Why do we have a string? Let's look at an example, right? This one we learned that already. But let's try this. If I put a big, very thick gallium nitride, what is the A? It's just equal to A0 of gallium nitride because it is relaxed. That's what we call relaxed. No stress. What is that? Can you tell me what is A0? I forgot to put here. Then we need to go to here. What is the A0 for gallium nitride? It's 3.189. Okay, so the lattice constant is 3.189 angstrom, right? See next slide. Now, what if I deposit aluminum nitride on top of it? The A now is still the A0 of gallium nitride because when I grow it, I need to match the lattice. I don't want to have any defect. I want to align them perfectly. So it is 3.189 angstrom. Is that okay? Make sense? But what is the string of aluminum nitride? Well, look at this equation. It's A minus A0 divided by A0. So aluminum nitride is 3.112. So I was 3.112, but you now force me to be 3.189 divided by 3.189. This is negative. Do you remember negative is compressive stress? But you don't need the number, you know already, because sorry, no, this is tensile stress. So I'm sorry, I did this wrong, right? It should be opposite. Let's go back again. C is the new lattice constant, right? So now it is stressed to the value of gallium nitride because I forced them to be 3.189. But its original value is 3.112. Right? So this is larger than 0, so it's under tensile stress. This is easy to understand because aluminum is smaller than gallium nitride. Now I try to align with gallium nitride, you are pulling me away, so I have tensile stress. As a result, this is going to give me piezoelectric polarization. I think I talked maybe too fast or whatever. Any question on this slide, what I have just saying? Any question about how I calculate, why I say gallium nitride is relaxed, why aluminum nitride is stressed, whatever? Can you follow what I'm talking here? Give you 1 minute. Okay, let me take a poll. Who can follow? Please raise your hand in your chat box. Who know what I'm talking about? Great. Also, please put no if if I'm confusing. Okay, right. So I think when you don't raise your hand, basically it means that you really, I was really not clear. Okay, let's do one more time. I have a wafer, gallium nitride. I say it is relaxed. What is relaxed? Just a crystal by itself. Okay, the atom just sit there in the equilibrium position, very relaxed. On top of gallium nitride, I'm going to deposit aluminum nitride. So if this is just a simple structure, if I have gallium here, I want to put aluminum nitride on top of me. I need to put in a way they're 1-to-1, right? Otherwise, they don't match the lattice constant. They will crack. So now this is not a real picture, but I think it is better to do it this way so you understand better. Gallium nitride is 3.189 angstrom. So when I put on top of it, what is this? Also 3.189. Okay? But originally, for a relaxed aluminum nitride, maybe I draw here. Aluminum nitride, aluminum, right? Not the right picture. I call this 3.112. This is the relaxed aluminum nitride. Do you get it? So originally, if I have aluminum nitride, their distance should be 3.112. But now I grow on top of gallium nitride. They got stretched, become 3.189. Is this part okay? Any question?
No.
Okay.
Great. Then basically this is what I'm trying to say. I have a released gallium nitride. Constant, lattice constant is 3.189. It's relaxed. This one grow on top of it, we call it pseudomorphic growth. Then it also have the same lattice constant 3.189. So it means it's under strain, right? The equilibrium position is 2.11. Now you pull me away. What kind of strain? You pull me away. It's tensile strain. This is the equation for strain. The new distance minus your equilibrium distance. Look at this one. You are going to use this in your homework or exam. So let's make sure. The new distance is A, equilibrium is A0. This is the strain, or C minus C0, right? So it is under stress. Because it's under stress, I have extra piezoelectric polarization. Clear?
Does the smaller space material always stretch to the bigger space material?
Now, that depends what is given to you. In this case, I say that gallium nitride is relaxed, and this is called the buffer. Whenever you have a buffer, we assume it is relaxed and everything else stressed to it. So you can think, what if I put aluminum nitride at the bottom, but gallium nitride on top? Then aluminum nitride is relaxed, but gallium nitride is compressed to the aluminum nitride. Is that okay?
Yes.
Okay, great. So this is given to you, okay? Now let's look at the system again. This is gallium phase. Gallium phase. So what happened? Now this is particularly say, okay, we put aluminum gallium nitride on top. I do something. Trust me that I can do it or I cannot, depends. If both are relaxed, right? Then what happened? Again, bottom is gallium nitride. So at the bottom, gallium nitride, I have about, this is gallium phase. I have three three negative polarization charge, right? Here, negative, positive, positive, negative, right? On the top right figure. So for aluminum gallium nitride, I have 1, 2, 3, 4, because I am larger, right? This one I mentioned here. Polarization, aluminum nitride is more than gallium nitride, just like what we discussed here, right? So this one you know already. So overall, this one gives me a positive polarization charge. And because of this, it's going to induce two-dimensional electron gas. Maybe one, let's say one, it introduces one electron, okay? Here, I give you another thing. Now the aluminum gallium is tensile stress, okay? You just trust me, I say it's they match, so it's tensile stress, like what I discussed here. They pull away, okay? By equation, you can use equation and you trust it, right? We don't have time to go through the physics. This tensile stress add an additional piezoelectric polarization. So originally it has 4, right? Now we have 5 because of this additional piezoelectric polarization. For the substrate, it's still the same. It's relaxed, so I still have 3. So what do I get? Again, positive charge, but now I actually induce more electron. I have 2 electrons because I have this extra tensile stress. So earlier, someone asked me, is this X going to change the polarization? It does. It changed polarization because it changed the spontaneous polarization amount and also the piezoelectric amount because you have different stress. Right. You're going to do this in your assignment, right? And maybe exam also. Let me ask one more time. Can you follow? Anyone think that?
Professor, can you just give a short review for the first A part? I just followed the B part, but...
Oh, the A part? Okay. Yeah. So if you can follow the B part, A part will be the same for you because now aluminum gallium nitride is relaxed. So I only have 4 positive charge, right? This is just example, right? It's relaxed. I have 4 because this is positive at the bottom and it's aluminum. So I have more, right? Gallium nitride on the top is negative. So I have less. So I have a net positive charge. So it's going to attract 1 electron. Is that okay?
Yes, Professor.
Yeah. Then when you go to P part, you have additional tensile stress. It gives you extra polarization, 1 more plus. So I have 2 electrons. I attract 2 electrons. Okay, and let me go to the bottom one now. Now I say, do you see that? Now we do aluminum gallium nitride. This is what you just asked. Some of you just asked. Now I put aluminum gallium nitride at the bottom, so it's relaxed. So the gallium nitride need to fit it, right? So it becomes compressive stress. Compressive stress gives me a polarization in the opposite direction. Right? So originally, aluminum gallium nitride will give me what? 4 negative charge, because now this is on the top, right? It was 4 on the bottom for plus. Now it's 4 negative on the top. Then how about
Professor? Professor, 3 negative, right? I mean,
aluminum gallium nitride, right? Not gallium nitride. So 1, 2, 3, 4 is stronger. Do you see? This material is gray. This equal to this. This equal to this.
yes.
Make sense?
Yes.
Okay. Here, how about now can you tell me how much spontaneous polarization charge is here for gallium nitride? Just spontaneous
3.
Say again?
3.
3. Right? We just follow the convention we had earlier. Okay? But we also have a piezo polarization, but in the opposite direction because of compressive stress. So this guy is gone because of this one. Okay, because it creates a negative. Or maybe better yet, how about let me do this? I call this negative, but right, because this is opposite. So how much do I get here? I get negative charge. Do I induce the hole or electron? 2DHG or
Electron. Hole.
hole, because you have a negative charge, right? How much hole do I induce?
2.
2 hole, right? It's just as simple as this to understand, right? Of course, this is useless. You cannot do any calculation. But that's it, right? So I leave the end phase for you. Go home, do it yourself, right? If you can do this, then you are okay. You understand gallium nitride system. Is that okay? Okay, now, then let's do some calculation. I'm a little bit slow, but I think it's worth it to make it clear, right? Very, very clear, because all this thing, it is either positive or negative. If you don't do it well, basically you have half of the chance to get it right and half of the chance to get it wrong. It means you have the maximal entropy. And basically it means you don't know anything, right? Because knowledge is about reducing the entropy. Now, how do I find? For example, now I have a system like this. What does it mean? It means I have a aluminum 0.33, gallium 0.67 nitride on the top and gallium nitride at the bottom. When I say that, it means the bottom layer is the buffer. It's relaxed. Okay? And then it means this one is going to get strain. Okay, because you need to match the lattice constant. So before all of this, I need to calculate the lattice constant. What is the equilibrium lattice constant for gallium nitride? Just check the table. A0 is 3.189. That's it. Easy. Okay. And then what is the equilibrium? I don't put 0.33 here for aluminum gallium nitride. Do you know? Can someone tell me?
3.1.
Say again.
3.112.
But 3.112
no,
for aluminum nitride, right? What will you do? You are almost there. Now you find that is no. What will you
add both of them?
Add both. Linear interpolation. Okay. 3.112 times x plus 3.189 times 1 minus x, where x equal to 0.33 in our case. Okay, so I just give you the answer, 3.1636. Need to be very accurate. When I was preparing this slide this Sunday, I spent 1 hour to figure out why my answer is different from last year. Because this time I forgot to put 3.6. I thought 3.16 is okay. But later you realize that the difference is so small. It gives you very different results when we do A minus A0. In your homework, you just use Excel. That is okay. But look, watch out for this. You need to go to 3.1636. Okay. Now, this is the equilibrium. We need the equilibrium because we need to calculate the string later, right? But anyway, now my question then, we want to use this equation to calculate the piezoelectric polarization. So this equation asks us to find the free E31 also, right? So how do I do that? Same, use what you just suggested, 0.6 times, I'm just to put x, 0.6x plus negative 0.49, 1 minus x. I use these two numbers. Okay, so this gives me negative 0.523. I need to put this because your assignment, you need to use this to double check your equation is correct. Otherwise, you won't get it right. It's very confusing. Okay, then I need E33 also. What do we do? Same, find this and then do it. 1.55 times x plus 1 times 1 minus x equals to 1.1815. Okay, anyone has questions so far?
So for E31 and E33, we take x as 0.33 or whatever the equation we get.
Whatever you have in that problem, or take x equal to 0.33 because here I give you x equal to 0.33.
Okay.
Yeah.
So basically that equation is like ALX J1 minus x, and that's it. That's how we get x is equal to 0.3.
Say again, basically the equation what?
ALX J1 minus x, and that's how we get x is equal to 0.33, right?
Yeah, AL, which is the, AL equation, AL value, aluminum nitride value times the x, and then the gallium nitride value times 1 minus x. And you do linear interpolation. Okay. How about C13? I just calculate all this, right? Because of time, let me just give you the number. It's not, doesn't worth the time to go through the derivation because you just use the same methodology, okay? I challenge you to do that. This is for you to check. If you cannot do it, let me know, send me the equation, I can double check for you. I do this because I want to calculate all this. Maybe I need to be very clear. I calculate this for aluminum 0.33, gallium 0.67 nitride. That is what I'm doing. Okay. Now, then what do I need to do? I want to see what is the piezoelectric polarization charge for aluminum. Let me make it very clear. For aluminum 0.33, gallium 0.67 nitride. What is that? I just plug in into the equation. 2 times. Now, what is A? Can someone tell me what is the A for aluminum gallium nitride now? So I'm asking, what is their lattice constant now at this moment in this system? What is their lattice constant? Remember, this is relaxed.
3.112.
Look at this system. This is relaxed, so the aluminum gallium trying to match the bottom. So what is its lattice constant at this moment?
The same as gallium nitride.
Right. So what is that?
3.18.
Very good, right? And then I minus A0. A0 is 3.1636 divided by 3.1636. This is the most tricky thing. Okay, and then you just do all the substitution. Okay, from here. I don't write it now. Right, just do this. Okay, so what is the result? Right, these are just math, right? So what we get is, let me check we get this one equal to, if you after done the substitution, is equal to negative 0.0299. Okay, this is Coulomb per meter square. Okay, now do you remember how do we find the electron gas? Right, 2DEG is equal to the piezoelectric polarization of aluminum gallium nitride plus the spontaneous polarization of aluminum gallium nitride minus the spontaneous polarization of gallium nitride. If you forgot, take a look at this picture. That's what we did just now. It's equal to the piezoelectric polarization, this extra one, plus the spontaneous one, this 4, minus the spontaneous polarization of the gallium nitride. And that gives you the electron density. Right? So what are they? First of all, the first one is easy, 0.0299. Right? The second one, we need to do some calculation because spontaneous polarization, again, need linear interpolation. So this term is 0.33 times negative 0.81 plus 0.69 times negative 0.029 for this one. Okay, and then this one I go to minus the negative 0.29 for gallium nitride also. Is this okay? And I'm sorry, I actually copied the wrong answer. This one should be negative 0.01272. Okay, so this one should be negative 0.1272. Okay, and this one is going to give me the total of negative 0.0299 Coulomb per meter square. Okay, maybe someone will find out my problem again this night tonight. Let me know. But my main point, the last point I want to tell you before the end is this is Coulomb per meter square, right? We usually will convert it to times 10 to the power 4 Coulomb per, no, actually minus 4 per cm square. Okay, and then we usually will divide it by Q, negative 0.0299 times 10 to the power negative 4 divided by 1.6 times 10 to the power negative 19 to get 1.87 E13 per cm square. This is talking about number of electron, right? Here is talking about charge per cm square. So you see that it's a very huge density. This is per cm square, not per cm cube. So that's why this high electron mobility, the GaN, has a very high electron density, very high velocity, and that's why it's very fast, good for RF application. Okay, I think I over time, but any questions I can answer.